All right, I think we're ready to get started. So I'll just start with a couple of announcements. So I don't know if you saw when you were walking in that there's the Grand Canyon University guy out there. So I was chatting with him. So if you're thinking about transferring to two-year university, which hopefully you all are since you're in this class, just think about other options. So I'm not saying, to go to Grand Canyon. Obviously, I know a lot of people go to SOU, but you could go to like any university. You just have to start, asking questions now about how to transfer and get all that done. But yeah, check him out. But he was advertising something, which I thought is kind of funny. So he was saying that you could do a class trip to check out Grand Canyon University, and it sounded like they paid for it. So we could get like 7+ students together, and then I could come along as well. So that could be fun if anybody's down for a trip. Just something to throw out and think about, especially because y'all are a large class, but definitely think about your future and where you're going to be going from here. And I'm always happy to talk about that individually. Don't forget to apply for scholarships, right? All that on your radar. So scholarships, internships, all the ships, right? Looking for summer opportunities. So again, if you want help navigating that, I'm more than happy to talk or write you letters of recommendation to do all this. But yeah, just, keep yourself moving forward in a forward direction. So just think about what you want to do next. Question?
I just got a link in the desk.
Oh yeah, you want to plug? Okay.
Yeah. Hello everyone. So Engineering Club is having a push to go to an event, not this Saturday, but next Saturday. It's going to be held in Central Point. It's called the Innovation Jam. It's being held at a makerspace out there. Essentially, it's going to be an all-day event. It's 9 to 5:30, and you're going to go there and get assigned a team in between RCC and SOU students, and you're going to be given a problem, and then you will have to create a solution in the time prepared, and then pitch that solution and prototype to judges. It sounds really fun. If you're interested in Bend, Oregon at all, this is going to be an excellent opportunity to get feet wet as a practice round. If you are interested, I can give you the link to our SVP, or there's flyers around.
Yeah, do you have an electronic copy of that, of the flyer?
I do not, but I can find it and send it to you.
Yeah, email it, and then I could post it in the announcements. And then, sorry, what day was that again, you said?
It is November 4th or 5th. It's that Saturday, 9 to 5:30. And there's going to be fancy food truck and lunch and everything there.
Cool. So yeah, get a flyer so I can post that, but then if repeating for the chat as well, so Innovation Jam on that November 4th was Saturday. So yeah, that's good. All things to put on your resume, right? So always reasons to get involved with clubs and activities. You put, hey, I went to this Innovation Jam, so you can talk about it. Any other announcements, questions?
I had a question about those reading questions in this week's folder and what those were for.
Oh, the inner chapters?
Yeah.
So I did, somebody else brought that to my attention. So I posted under the announcements, the inner chapter link. I forget that those aren't in the textbook, but it should link. And they're just like a lot of history things, so. But I'll save that. Yeah, so it'll be the same just with these different chapters. And if people need the due dates extended, I can do that, but I usually let it, I mean, it should still let you take it after the due date, so the due date shouldn't matter. But, so in case you're behind on that. Other questions? And we do have lab this week, so I printed out the lab, so it's a spectroscopy lab, so that should be kind of fun with the light absorption. So we'll talk more about the colors, so we'll save that for lab. And then, so I have a bunch of stuff to hand back to y'all. So I am caught up on grading, except for the online submissions. And then I didn't finish grading your quiz all the way. I'm like halfway through. But otherwise, so check your grades, make sure that they are accurate. But I wanted to go over some of the questions, because there was one that was missed a lot on the quiz. And so let's look at it. So which of these atoms has the lowest first ionization energy? And the answers were boron, aluminum, magnesium, and beryllium. So take a moment to think about it. So you can pull up your periodic table. So you're thinking about not only the trend, but then, right, the orbitals as well, and how those might influence your answer. Then if you're in the chat, I'm watching the chat, so you can type out your answer. Let's see. So I see two different answers in the chat. So what are we thinking here? So I'm hearing some aluminum. I see aluminum in the chat. And so let's look at aluminum, and let's look at our periodic table and kind of what the trick was. So what's the trick here, and kind of what was our general trend, but then what's the difference as we go, right, from magnesium to aluminum? So single electron in the 3p, and so that's a good explanation, and it's exactly. So we're comparing the aluminum to aluminum plus. And so that transition, so we're just taking one electron from that higher p orbital. Oops, that's a 3s. Oh my gosh, sorry. So we took that electron away. And so if we compare that to magnesium, so of course magnesium, let's look at our periodic table. So it's in the same row here. So still the 3p, 3s, but of course it doesn't have any electrons in the 3p. It has these paired ones in the lower 3s. So that's why it's more favorable to take it from the higher 3p versus trying to unpair those to make our cation there. And so yes, that's why it makes it slightly lower. And then other answers in the chat. So boron, but then we have to compare, right, boron versus aluminum. So you could do the trend. So the same trend happens between beryllium and boron. So boron has a lower ionization energy than beryllium. But of course, since aluminum, right, slightly larger radius, a little bit further out, so that nucleus has a slightly less tight hold, so it's easier to remove the electron in the aluminum compared to boron. Yeah.
Is this common for all of the blocks, like between, say, like S block and D block? Like that jump, it's more favorable to take an electron from the D block than the S block?
Kind of, but so remember this one gets weird sometimes, so we saw like weird patterns, so it depends if it's more favorable to fill up maybe all 5Ds and then you take one from the S, right, and then that's where the electron then comes out of the S sometimes. But yeah, that gets a little trickier since the d orbitals also, like we mentioned, go with different geometries. But yeah, same idea though, right? So it could be, as long as it's energetically more favorable to take it from that energy level, it could happen. Yeah. And so we mentioned, right, general trend, it increases as we go across the periodic table, the ionization energy. But yeah, it's just this weird trend as we go from magnesium to aluminum. And then we also saw that, right, with nitrogen and oxygen, how that's a little different as well. Maybe we should look at those notes if I could find them. No, I'm not going to be able to find them. Anybody remember where the energies were at?
Couldn't tell ya.
It might be faster if I Google it. So I was trying to find this chart again in my notes. Oh, not that. That's not what I want. This chart.
Oh, that's in chapter 4.
So maybe if I look through my chapter 4 notes, but again, that was that same little oddity. So there's the oddity in aluminum that we were looking at. So now we can see with this chart, it's really obvious that it's aluminum. And so again, that's going from the S to P, but then we see that weirdness where it drops going from, right, nitrogen and oxygen, and then the same thing, phosphorus to sulfur. Since it's more favorable, right, with oxygen. So if we draw this again. Oops. And so another oddity from the trend. Just do first ionization energy. So we compare nitrogen versus oxygen, so we can do the same thing. So we draw out nitrogen, so they're both in the 2p. And so, of course, oxygen has 6 valence electrons. And so this is where it's slightly more favorable to remove an electron from oxygen compared to our nitrogen here, since nitrogen, they're all happy, they're unpaired, so remember we have to pay a price for pairing. And so it's actually happy to get rid of this and go back to only one electron occupying each orbital, so that's happier compared to messing this up and then removing one electron from our one electron filled P, and so now that's less favorable energetically.
So it is better to leave paired electrons as they are, because they like to be paired when each of the shells are filled.
Yeah, so it depends if they're like
But if it's
filled.
just one shell that's filled and the other two just have one electron in it, then it's better to take the
Yeah.
paired one.
Yeah,
Okay.
yeah, and then once you get to the scenario, right, with fluorine and neon, right, those are all like more paired now, so that's unfavorable. So it's just with this like one electron oddity, and you also have to compare it to where it's going, because again, we're comparing where you're paying the price of energy versus now every electron will occupy one p orbital, it's happy now, versus, right, they were already happy being unpaired, and now we're going to pluck one out, so that's not really energetically favorable, like we're not gaining anything from that. All right, good questions. So let's look at some more review questions. And so of course, right, just know your subatomic particles, and we'll do some practice, but so protons, neutrons, electrons. And so let's calculate, or how would you know this? So which object has the longest de Broglie wavelength? So is it a proton, an electron, or an argon atom, or Spider-Man? So
Last time we used this calculation, we did it on baseball. What is exactly, does that mean when you're trying to baseball, baseball, move, moving side to side, like wheels? Or what exactly does that mean?
So we're calculating, right, the de Broglie wavelength of an object, so kind of, right, it's motion. But we're trying to, I'm getting at something with this, so we don't have to plug in a bunch of numbers, though, is what I'm saying. So we did calculate it at one point, right? We can do that. We can calculate the de Broglie wavelength. But what did we show with those calculations? What was kind of the point of them? What do we remember?
Like stuff on the macroscopic scale has tiny wavelengths.
On the what scale?
On the macroscopic.
Yeah, macros, yeah. I was making sure I heard right. So, right, so exactly what he said. So on the macroscopic scale, like, so Spider-Man, right, has a super tiny de Broglie wavelength, so it doesn't matter. So that's what we were saying, right? So that was the point of the baseball versus the electron, is that we throw the baseball, but its de Broglie wavelength is so tiny that it doesn't matter, that we can just calculate its trajectory using classical mechanics. So that's why we don't talk about, uncertainty in quantum mechanics. But then we said, right, so of course as things get smaller, and then we calculated their de Broglie wavelength, and it was about on the order of their size, right? So now your de Broglie wavelength is your size, so now that's when you exhibit quantum properties and start behaving like an electron behaves, where it behaves like a wave and all that. And that's why it matters at the tiny scale.
So you're saying on just like a small, like sub-nanometer, a baseball is actually.
Yeah, but I think it was even smaller. So the nanometer, I think, was what we calculated for the electron, and then it was like, I want to say to the negative 30 something. Like, it was ridiculous. Like, but yeah, but that's basically it. It's like it's acting like a wave, but it's so small that it doesn't matter. So then, does anybody remember the formula, or do we at least know who would have the longest de Broglie wavelength out of these options?
It would be an electron, because it's the smallest physically.
Ding, ding, ding. So it's the smallest. And so, right, I could have thrown you off and started giving you like masses of everything, and then you would have been punching like crazy. And so what's the formula? Does anybody remember what the de Broglie wavelength formula was? So wavelength equals h over momentum, which was mass times velocity. So excellent. So yeah, so we didn't have to do a bunch of math. We could just see that, well, at least with the mass, of course, right, the smallest one is going to give us the larger wavelength. All right, so let's do another question. So which of the visible colors has the highest energy? I could give you answer choices, but you probably don't need them. So Tony in the back.
C, purple.
C, purple. And do people remember the little mnemonic for the colors in order? Roy G. Biv. And so good. So purple goes in with indigo, violet. So it's actually funny. If you look into it, it's like historical reasons why there's that many colors in the rainbow. Like somebody was just like, yeah, I'm going to make these two distinct colors. So you could argue about that, but whatever. Anyways, so purple, right? And this is closer to ultraviolet. So that makes it smaller wavelength, higher energy. Good.
What if one of those was white?
But white's all the light, though.
Yeah, so what would have more energy?
I think it would still be purple, because white would be like offset by the average of like red.
Yeah.
Because isn't white light like most similar to like the yellow range in terms of like wavelength?
But it's
Size.
literally all of them, though. So it's only when you split them with the prism that you can tell, right? So because that's what the rainbow is. It's just white light split. So.
I think it depends too, because we were talking about this yesterday about how the sun is white and it emits white light, but it has a slightly more blue light.
Mm.
White light
But-
isn't visible. It's just a combination of a whole bunch of here's visible.
Yeah. All right, let's do some quantum number practice. So now we can go, gotta measure the sun. So determine which quantum numbers are valid and correct. If incorrect, so 6, 3, 3, negative 1/2, 3, 2, 1, 0, and 5, 5, 2, negative 1/2. Are we ready to go over them? And so looking in the chat as well, so what do we think about the first one? So thumbs up, I see a lot of thumbs up. So looks good. So what kind of a orbital is it referring to?
Is it a 6F orbital?
So yes, so our 6F orbital, something crazy. And what about our next one?
It's a 3D orbital, but it doesn't have anything in it. There's
So
no
what-
electron in it.
So invalid quantum number here. And so let's change that. So we could have changed it, right? -1/2, +1/2. Either one of those would be appropriate. And so let's write, so it's a 3D. We didn't have to do that. Any questions on this one? And what about this last one? Any issues? What do you say?
The L number is theoretical. So does that make it invalid?
Yeah, so we have, right, a 5 here, but it has to be n-1. And so we could just say, 4 would be appropriate or anything. So as long as it's valid. So then, right, technically it's a G, 5G orbital or something crazy. Any questions on those? All right, let's try another problem. So a new element has an atomic number of 132 and a mass of 288. How many protons, electrons, and neutrons are on an atom with a -3 charge? People have answers.
So we would have 132 protons.
Woo, hang on. Oh, you guys are fast. All right, 132 protons. That sounds good. Oh, question?
Oh, no, I have the next.
Oh, answer. Next answer.
It's gonna have 96 neutrons.
96?
Yeah, I just did 288 minus
Oh, I put it in my calculator wrong, that's why, I was like, what?
Oh, I was doing sanity check.
They're about the same max.
Yeah, 156, yeah.
Yeah. So you could kind of do, it's like roughly half, so do mental math check. It's always calculator errors. So 156, so looking in the chat as well. And then electrons, what do we get?
It's going to be 120.
Like 135 if it's the -3 charge.
Yep.
Again, normally it would have, if it's a neutral charge, it would have 132.
Yeah, excellent. So 135 with that charge, so you're adding electrons to it. Questions on this one? All right, so then you might get some conversions as well. And I would expect them to be like random potentially. So convert 467, let's do nano goops to floofs. And so if there are 19.5 goops in a floof. So CV can figure that out. Like your definition, you guys are gonna define how many moles of goops.
How many moles in I got 2.3. Yeah, they did not schedule it.
What did you say was their answer?
2.3.
Question, answer?
Answer.
You want to, although I don't know if we have a functioning marker.
There is a marker sitting on the board. Cannot confirm or deny if it works.
It's a neon marker, but let's see.
Let's see how bad this works.
So.
Oh, it's
that's
actually,
excellent.
yeah, that's shocking. And so chat, you can post answers as we work through it. And then what's the exponent again on nano? What does that mean?
Nano.
So I hear 10 to the negative 9. See it in the chat too, negative 9. So it looks good. Just gotta set it up. I like our goo.
Nano goo. So, one goo is the same as this many nano goos.
So that looks good. So setting up your conversion. And so goops has to go on bottom. One floof on top. Then, so on the board we have 2.39 times 10 to the negative 8. Oops. Floofs. So is this what other people got? Thumbs up, thumbs down? So I see a lot of thumbs up.
I also got a different exponent, but I don't know what I did wrong. Because I'm assuming Vaughn's right. Because Vaughn's better at doing conversions than I am.
I would check calculator error. Negative 12. And you put the 19 on bottom. It's 19.5 goops.
Yeah, I'm getting, with this conversion, I'm getting.
So do you get that when you plug it in for the first step?
Are you using the right E? Because there's two of them in the calculator.
Yeah, you could write it on the board, but you have to be careful. So I don't know. Because if, yeah, well, at least that gave me a really weird answer, so I don't know.
I think I see what I did.
So I just started by converting.
Either way.
Right? If I move the, so now oops,
I think it should be 10 to the negative 7, though.
oh, did I go the wrong way?
I think so.
Okay, then that's why. Wrong. Okay.
And I see what I did wrong too. Instead of doing 10 to the 9th, I did 10 to the negative 9 for the first conversion.
Yeah, that makes a difference. I originally wrote it down as that, and I was like, wait, because you gotta think like in your head, like one of a thing versus
Many of a
many
different
of
thing.
a different thing instead of a small fraction of it already a very small thing.
Okay.
Yeah, and then Tori, if you're doing it your way, so you could just plug it into the calculator, so 1 times 10 to the negative 9, right, to get your nano, so then you're starting with the converted, and then you can do the goop floop thing. Yeah. Any other calculator mishaps or questions, converting issues? Do another practice.
Please.
So we'll do a normal unit this time. So convert 457 inches squared to feet squared, and just in case, so 12 inches is 1 foot. And looking for answers in the chat. And then, Tony, were you volunteering to put it on the board?
I mean, I'm pretty sure I got it, yeah.
Yeah, go for it. And if you didn't, it's always a learning moment. Yeah, we're going with the blue today. I see an answer in the chat as well, so we'll see if it agrees. And don't forget, you gotta, are you gonna square them? Don't forget, you gotta square the 12 though. You have 38.
Yeah.
So, but remember, you gotta square it. Remember, you gotta square the 12.
I got all the together here. I got the squares together over here.
Yeah, so then you gotta go 1 squared, and then what's 12 squared?
All of them are all cancel out each other here with how they're both squared up. But inches squared and feet squared.
Yeah, but your conversion factor is in 1D. That's what I'm saying. So you
I
can't.
have a 2 up there.
Well, you can't just put a 2 though, is what I'm saying, right? Is we can't just say 12 inches squared equals 1 foot squared. That's not.
And if we think about, 12 inches, it will not look, the 12 inches squared will not look like squared. Yeah, anyway. Yeah, it would look.
Yeah, because you got to square, right? Because this is just in 1D when you're doing it. So this is a 2D factor, so you just have to square the 12 as well. So then you get 457 inches squared times 1 foot squared, and then distribute that. So 12 squared is 144 inches squared. So that's the conversion factor.
And then that's like, what's that, 2, 3, so ish.
Yeah, the chat has 3.17 feet squared. Is that what I see? Thumbs up. So more thumbs up. So yeah, watch those. That's why we practice this one though, because.
Razor doesn't like this marker, by the way.
Oh, that's fine.
Well, not very well.
I think there's spray somewhere.
Probably somewhere.
So let's try another one, since these are tricky. So now let's convert 8,675,000 centimeters squared to meters squared. And so 100 centimeters, 1 meter. Does someone want to throw it on the board for us? Looking for answers in the chat. Oh, we'll give Madeline a turn at being a victim.
Victimizing myself because I'm bad at this.
It's good.
The whole thing in parentheses and square it, and then that equals 867.5 meters squared. If anyone can see this still.
Yeah, that looks good. I'll rewrite it since now our marker is fading. And I see it in the chat as well, so they agree with your 867.5 meters squared. And let me copy it, sorry, being slow. And so again, good job squaring that factor, so don't forget. Questions about this one? All right, let's try another one. This is a different type of problem. I can't remember if we've done this in this class. If not, we'll go over the trick, of course, but see if you can figure it out. So gallium has 2 isotopes. And so the average atomic mass is 69.723 AMU. And so gallium-69 has a mass of 68.9255 AMU. And the other isotope, so gallium-71, has a mass of 70.9247 AMU. And so what is the percent abundance of each? Okay. I thought you might have seen it, but I couldn't remember. So let's see if you remember.
Did you say that 71 gallium was 70.9241 or
47.
927? Okay.
9247. Do we have answers, thoughts? So do we have any thoughts on how to do this? Do we set it up? Does anybody know the setup or maybe how we can work through it? Yeah, 1 minus x. Perfect. So that is the trick. So we could go back, right? So x plus y gives us 1, since we convert, right, our abundance from 100% to the decimal for the math. And so that's how Tori ended up with this equation there. So then I would say the first step is at least a setup. So if you can get the setup right, you're in pretty good shape. So that means we have our average is equal to, so we set that one equal to x. So our mass times our abundance. And right, we can only do this with 2 isotopes since we can't do 3, too many variables at that point. So we'll keep it simple. So plus 70 times 9247 times 1 minus x. And so this is your step 1. So can you set this up? So that's important. And then, of course, from here, it's just write algebra. So just distributing this x, distribute this 70, right, times 1 times negative x. And we can walk through that. So I'll write on the board, or right here. So plus 70 minus 70x, blah, blah, blah. So now do the math. So I'll put 70 on this side. So now we're just calculator clicking. And double check my numbers. So I have negative 1.2017 is equal to, so I gotta do the x subtraction now. So 68.9255 minus, so that 70. And try not to make any calculator mistakes myself. So then we get negative 1.9992x. And so then we can solve for x, so our negatives cancel out. And so that's about 60% roughly. So 60.1% or so, or 60%. And then, of course, we can just do the subtraction. So then that leaves us with the 69% for gallium, or sorry, 60% for isotope 69, and then gallium 71 would be, 39.9%. So questions about that one?
How did you get the negative 1.2017?
The negative 1.2017, that was from subtracting the 69.723 minus the 70 to put all the numbers on one side.
Okay, gotcha.
Questions about that one? Okay, let's try another one. So now let's say a cylinder has a density of 15.3 grams per centimeter cubed and a mass of 21 grams. So given the height is 6 centimeters, what is the radius? And I will give you, so the volume of a cylinder is pi r squared times h. Do you have an answer? You wanna, I hope that marker is still functional. I would like you to put on the board.
Go up to CS and grab
Yeah, I think I forgot extra markers.
That's a, so I,
Walk us through.
yeah.
What do you?
First, I'm getting the volume of the cylinder, and then I'm going to do a second equation after that. So, 21 grams, we know that the density is, per 1 centimeter cubed, we have 15.3 grams, which makes this 1.37 grams. Technically, actually, it should be 1.4 cubed for the sake of it, but I'm just going to use the whole thing in my calculator. And then we can equal this as the volume, and then I squared times the height. Then we're just going to divide by pi and the height, which we know the height is 6. So it's pi 6. Pi 6. And then that leaves us with a decimal value equaling our radius squared, and we just square root both sides, and you get the answer of a radius of 0.2627 to a 6
Oops. I feel like it did something.
Hold on. Oh, never mind.
Oh, I
Doesn't
did.
matter.
I did something wrong. Yeah. That's. I have the answer in my face.
Yep.
That looks
I
good.
was
Sorry.
canceled and thought I didn't cancel out the centimeters cubed, so that was wrong.
Yep. So that looks good. So excellent. Does anyone have any questions on that? Yeah.
If something symbolizes on the midterm, are you going to give us the equation again, or should we write this down?
No, I would give you. Well.
Like the cylinder.
Yes, I would give you a cylinder one, but it may be a square. And I don't remember if I gave you that explicitly, but that would just be length times width times height, if that's indeed on your exam. Do we feel okay about this type of problem, or? I see thumbs up.
Can we do another, the abundance percentage ones?
Another percent abundance. Okay. Let's see if I can make up. So let's see. So an element has our two isotopes. And so its average mass is 132.55 AMU. And so it has two isotopes, so isotope 128 for element X, which has a mass of 128.2234 AMU. And then it also has atomic number 135X, which has a mass of 134.9987 AMU. So what's the percent abundance of each again? Does anyone want to put this one on the board for us? We can look at it. Also looking at the chat again for answers. On any other volunteers? You want to do it? Audrey, we'll let Audrey do it. And then we'll have you double check numbers. We'll looking for chat as well to help us double check.
I assume it comes up when we get the fractions, but it's not distributed all the way.
So copying it. So that looks good for the first step, and then I just didn't do it. See, that looks good. So negative 6.7753x it looks like. And if people disagree on numbers, let me know. X is equal to.
Oh, I didn't write that.
So what's X 36.1%? 36.1%, and so that would be for 128. Is that what other people got? I see thumbs up in the audience. And then does anybody need to see anything more explicitly, or we follow along? So we should follow the sig fig rules, but I've kind of lost track of it with, yeah, because I think you should end up with a lot, because we have like 5 from our answer. So then we should retain 5, but it's okay, we truncated it. Other questions?
Could we just go over some more quantum examples?
So quantum number, yeah, we can do that. Because we also have, there might be some balancing equations on the exam. So let's do some more. So let's do, are these valid numbers? Try those 4 out. Are you ready to go over these? So what do we think about the first one?
It has too many orbitals.
So too many orbitals, and so we have N, L, M sub L, and M sub S. So which number do you have issues with, or what can we
M
do?
sub L.
So M sub L, so should be 0, since we only have our one S orbital. And you could have gone crazy and changed, right, your N and your L, but you would have had to change both to accommodate that M sub L. And then what about this second one? What do we think?
The L value is too much because it should be minus 1 minus.
Yeah, there's no such thing as a p orbital with the s
Good.
block.
So yeah,
In the
there's
first
no
energy level.
1p violates the rules. Good answers there. And so you could also write changes to a 2. So I'll just put, right, more alt answers. If you had changed it to 2, 1, and that's fine for it to be 0. So that didn't matter. So that could be another alternative. And what about this one? I see thumbs up. So yeah, looks good. And then this last one, any issues with this one? Excellent. So we have our L is 1, so this is too big, or at least what he was saying, the absolute value. And so it doesn't work. So we could easily just change this to 1, or -1 would be appropriate, or 0. Or we could, have changed the L as well. So I'll put that as another alternative answer. So if we change it to 3, 2, -2, that would also be valid. Excellent. So we feel better about those. Let's just do, so now just what I have left on my prepared review is which has a higher ionization energy, so phosphorus versus sulfur, but we kind of already did that. We could do it again, but I think we already did it, but I'll save this for the end. I'll just write this down so it's on your radar. So phosphorus over sulfur. And remember, we said the answer was phosphorus due to that pairing. So I won't belabor that unless we need to. And let's just do some balancing practice. Oh, question?
Yeah, I have a question about the ionization energy. Just to clarify, because in my notes I have it's harder to unpair electrons than to take and keep one, or take the one away. But that only, I guess. So does that only work if the whole
Yeah, so
orbital is
so there's two things with that. So right, we have to pay a price when we pair it, right? But then we find that when they're in the orbital complete, that they don't want to be unpaired then. So yeah, when we're talking about, so if we do phosphorus versus fluorine though, right, that's a little different scenario because now all the orbitals are getting filled up on fluorine, right? So now it has almost all of them complete versus phosphorus, where it just has, right, the 1. So now fluorine has a higher ionization energy since it's so close to being filled. And yeah, we have these paired electrons. And it does get kind of weird because yes, you do gain some energy back, right, from the unpairing, but it's still unfavorable because we're almost to the complete octet. So it's really only weird when you go, right, that group either 2 to 3. Sorry, where's my periodic
So
table?
would fluorine then Or
Or
would it
you
s-
mean from like sulfur, if we were talking
Uh,
about that case?
Sure.
Because we're just comparing them like, we're just comparing the ionization energy, right? So you always have to look at where it started versus where it's going, right?
Mhm.
So that's also what you're looking at. And so in this case, right, it's not phosphorus. We pay a higher price because they were all filled. Now we're getting rid of one. Versus, right, fluorine positive. And so, right, we eject it, right? But like you're saying, so fluorine is almost filled though, so it's pretty unhappy to do that. So it takes a lot of energy, and it's also with because there's a lot of factors with it, right? Because we have our general trend, but it's also as we fill it more electrons in this 2p orbital, right? There's more of an effective nuclear charge that keeps it tighter, so then it takes more energy to kick it out there anyways.
So then it would be more energy intensive to take the electron from phosphorus in this case, because it has a half-filled orbital.
No, it's fluorine still more, has a higher ionization energy though, because it's almost filled. So that's where, yeah, and so I may have misspoken or gotten something fuzzy, because, right, you pay a price, you always pay a price for pairing, right? But then you're also considering, like, what orbital it's coming from and how, like, filled up it is. So that's why we're saying, like, when the phosphorus versus sulfur case, right, we paid that energy price to have sulfur, right, with the paired electron in this one. And so in that case, it's happy to get rid of it because it's still in that same orbital. So it's still in the same 2p level. So then it's going to gain energy back from that pairing price. Yeah, but then now once you get to fluorine and more of it's filled, like, yes, you still pay that price for pairing, but because you have more electrons in there and you're so close to the octet rule, that's actually outweighing it. So, yeah, that's why we call these oddities, right, with phosphorus and sulfur, because it does violate that general trend of increasing across because of the effective nuclear charge. All right, balancing practice. Let's just try, we'll try a hard combustion one, since those are always, oh, no, I probably wrote too large. also looking for answers in the chat. People are still playing. So let's just shout it out. So lead us off, Alira.
Oh, I got 2 C6 H14 plus 38 O2 to 12 CO2 plus 14 H2. I think my math is
Is that what people got on the O2? That's the only thing that I was.
yeah 24 is so 12 times 2 is 24 and 14 plus 24 is 38.
So then that's 38, but then it's O2, right?
Oh, so that'd be 6.
Yeah, so it should be 19. And Tori, is that what you got? I saw you be at 1902. And you all.
Is there, do you know if there's some way to solve these inequalities, like, figure out if there's a way to set this up to make it easier? Just trial and error.
It usually just ends up being trial and error, unfortunately, because you want to leave oxygen. Like you can try it at the end. So I would just like start playing with the carbons first, because the carbons are only in 2, and then you kind of go from hydrogens. But yeah, I think it'd be harder to do algebraically. You kind of just guess and check. And then so it's better to balance with the whole numbers. And then if you were to be given like a multiple choice question of this, it might phrase it right. What is the sum of the integers? And usually this isn't a problem. So in this case, right, it was like 2, 19, 12, 14. But if you have a 1 coefficient, sometimes that's where people get tripped up if I ask questions like that. Yeah. So don't forget to add the 1. I don't remember though if I asked it like that or not. So yeah, it should be 2, 19, 12, 14. You could have done like 1, 19 and a half, 6 and 7, but it's just better to use the whole numbers. But so make sure you distribute everything and go back. Let's do another little practice on balancing at least. So we have rubidium nitrate plus beryllium fluoride gives us beryllium nitrate and rubidium fluoride. So see if you can balance that one. And let's see, people still. Yeah, or you could just shout it out. What do we have?
So you're going to need 2 rubidium fluoride.
Oh.
So 2 rubidium.
And
Sorry. I was just gonna do it in my head. 2, yeah.
And then 2 of the rubidium, is that nitrate?
yeah.
And then, yeah, 1, 2, 1, 1, 2.
So that looks good. And then if we were answering right the sum, so 2 plus 1 plus 1 plus 2, so what does that give us? So 6 for our sum. So don't let those 2 1s trick you. Let's see, there might be temperature conversions too, but I would give you like the formula and then you could plug that into the temperature. Do we have other questions or requests? Topics? Yeah. Should have. Trying to think of some cool equations. Yeah, so let's try this one. So see if you can balance it. So this used to be what was in automobile car bags. So it makes a reaction of sodium plus nitrogen gas, at least for the first step. So see if you can balance that one. Let's give people a minute or so. And so what do we get when we do this one?
We got 223.
2, 2, 3, is that what everybody got? 2, 2, 3. And then, so we could do one more practice. So this is half the story with the airbag. So this is, again, the old material. So not the bad stuff. We'll go on a little aside on what that was. So this is the first half of the reaction. So sodium azide decomposes. So notice the product, though, is sodium metal. And so what also had to go in there, so see if you can balance the next step of what was going on in the airbags, is that they added potassium nitrate to go ahead and react with the sodium, and it makes this intermediate product here. Correct, you could split it up, exactly. So sometimes it helps to keep it together, but then, yeah, in this case, you can tell it got blown apart. So what do we get for the coefficients on this one? I think, what are other people? What'd you get?
10 to 1, 5, 1.
So 10, 2, 1, 5, 1. So that should be correct. So double check everything. Make sure you distribute. Is it Na2O? Okay, did you find your error?
Yeah.
So this was a tricky one. And then if we want to just do this for completion's sake, so this one might be easier to balance. And so what's even crazier about this reaction with the older generation airbags is this was the intermediate step. So the final products, where then it goes on to react. So they also put silicon dioxide in there. And so it finally gave the final products of this potassium and sodium silicates here. But the safety issue with that is that these are really hot. So, right, you have to be thinking about impacting. So this reaction happens and it's quenching this molten sodium that's being created. But then the problem is this potassium and sodium silicates were still really hot and burning people. So that's where they went to the alternatives. So once you balance this, and we'll at least look at the fun history lesson of airbags. And so what do we get for the coefficients on this one, or what do we need to do? 1, 1, 2, 1, 1. That looks good. Just looking for thumbs up. And so just while we're on this topic, I'll share the article. So this was the first generation. And then do people kind of remember those Takata airbags that were under recall? And so what happened with that is they decided to change the sodium azide and put ammonium nitrate in there, which is a fertilizer, and maybe you've heard of like ammonium nitrate explosions. But what happened, and so this is interesting where you always got to pay attention to your chemistry, is so the ammonium nitrate is more sensitive to humidity, so this was especially prevalent in like humid, hot areas. And so that humid air, so the moisture would get in and kind of start solidifying this ammonium nitrate, so it would like get it all wet, and then it would turn into one big piece. So they called it Oswald ripening, but that's more of like a crystallization process is what it's referring to. But then when it crystallized, it left these channels. So basically when it reacted way faster, way more violently than they had originally engineered it for, and so that's where it was blowing out that shrapnel. And so then they talk about how now they have this chemical is now what's the choice in the modern airbags. And then they have also gone back to the compressed gases. So this was something they tried like originally when they were exploring how to make airbags, but then they went to the chemical propellants. But I guess now they're experimenting, doing some hybrid. So that's this fun fact. All right, I guess that ends our review. So let me know if you have more questions. Of course, I can answer them, and then I'll see half of you in the lab. Oh, yeah. So I'll leave this series up.
Curious where I went wrong on this one. Did I write it down? C6, H12, C.
Oh, yeah, H14.
Oh,
That's
that's
what.
it.
Oh,
Okay.
no.
I know, I half the time it's that or
I
something
know.
else. It's just
Transcription
transcribed the
error.
wrong way.
Oh, yeah. Thanks for picking that up. All right, any other questions in the chat? I'm gonna end the stream soon. Just waiting for questions just in case.
So I finished this week's homework, but I'm just wondering if I could like keep it to study for the test.
Oh,
and
yeah,
write
that's
notes on the
fine.
test. Okay.
Yeah.
Thank you.